talk about my specialty, which is 3D climate circulation, and here specifically on habitable worlds, which means solar system and beyond. And to understand 3D climates, it's always useful to go to the Earth because, I mean, that's where we are, and we know it's habitable, and we know that the 3D climate dynamics is very important to understand the habitability of this world. And here specifically, I want to point out that what we are doing with 3D climate dynamics is basically we are conducting research in fluid dynamics in the atmospheres of planets. And here I give you an overview of the Earth, where we see the total rainfall of different locations. And you can already kind of see that there are some stripes in longitude. For example, here at the equatorial region, you see it is very wettish, so I have a lot of rainfall. And just north and south of it, you actually have a pretty dry regions. And this is directly tied to the circulation cells of the Earth. So the Earth has 3 circulation cells. The Hadley cell is a tropical cell with very wet upwelling branch that is responsible for the tropical wet climate regime. And a dry downwelling branch is responsible for many of the desert regions in the Earth. So there you already can see locally the impact of circulation. So circulation really determines where the water, for example, goes. And some regions are more or less habitable. And the width of the circulation cell and the number of the circulation cells depends mainly on the rotation period of the planet. We can shift it a little bit up and down also with temperature differences. But in principle, if you know the rotation period of a planet, you also basically know how many circulation cells the planet has, which is important to understand already basic things like clouds and surface liquid water distribution. And you can actually look at the tropic Hadley cell as a kind of heat tension. So you have this fluid dynamic solutions where you basically, transport stuff around, but on the other hand, you have heating from the star, so radiate the atmosphere from above. At the same time, you also notice that because the solar valuation comes in more or less parallel, that regions that are relatively far north or relatively far south basically spread the incoming radiation over a greater surface area, which means that heating in these regions is less efficient. And that creates a surface gradient, so from the equatorial to the polar region. That is a driver of climate dynamics. On top of rotation is extremely important, because it determines basically how far north a wind jet can go from the equator to the north region. The heating leads to upward rising of air masses. The air masses radiate then in the upper atmosphere towards space. They cool down, they lose water vapor, they get down to the surface, and they flow back basically towards hotter regions, and then we have a closed cycle. And that also shows you in principle that climates can also have to be understood in the framework of astrophysics. So how much stellar flux is coming in. And here a very important principle is the habitable zone. I have to point out, as always, that the habitable zone just tells you that there's enough stellar flux coming in to allow, in principle, for surface liquid water. It does not tell you per se that the planet really has surface liquid water. That really depends strongly on the atmospheric composition. This also is a little bit pointed out here by this review by Sarah Seeger, that if you have a purely Earth-like planet, the habitable zone for different type of stars is this bluish region. If you dry the planet out a bit, in principle, you might even extend the habitable zone a little bit inwards. On the other hand, if you have a rocky planet with a moderately thick hydrogen atmosphere, hydrogen can be a very, very efficient greenhouse gas. In principle, you can even extend the habitable zone indefinitely outwards if you have some kind of internal heat source. Because in that case, the hydrogen will keep basically the radiation from the planet from escaping to space and keep it warm. However, for a truly Earth-like planet, we also need to understand 2 other very important cycles. And this is the water cycle on the left, which means that you have to have some kind of equilibrium between condensation, evaporation, and surface liquid water. And if you don't have this, for example, on the Earth, you can, in principle, put all the water oceans into the atmosphere, and then you have surface pressures of 260 bar, which is not nice for life, and surface temperatures greater than 900 degrees Celsius, which is even less good for life. And the tipping point, actually, towards this regime for the Earth is when it's estimated to be when the average surface temperature is a bit above 50 degrees Celsius. Because what that happens is that you evaporate so much water that the water vapor is a very powerful greenhouse gas, which means you warm up the atmosphere, which means that you evaporate even more water, which means you warm up the atmosphere even more, and you get in this runaway greenhouse limit and evaporate eventually all the water vapor into the atmosphere. And the next thing that goes is the carbonate silicate cycle. So the water cycle is actually embedded in this carbonate silicate cycle. And here it is important to note that even on the Earth, there is about 8 bar of CO2 bound, fixated in the crust, and several tenths of bar in the mantle in total. And you need surface weathering, which means surface liquid water on the land mass, and transport of these carbonates into the bottom of the ocean, and then plate tectonics in order to deposit CO2 from the atmosphere, and then the volcanism outgases the CO2 into the atmosphere again, and we have again a nice cycle where, luckily for us, this carbonate silicate cycle together with the water cycle keeps the Earth at about 300-400 ppm CO2, but not in all circumstances. And treated climate science is here important because, yes, it is computationally consuming and nonlinear, and sometimes also difficult to interpret. However, it is really absolutely necessary when you want to understand the stability of these major water and carbonate cycles, and if you want to understand these tipping points of cycles, when you can tip over to more and less habitable climate states. And for the Earth, actually, it is a very important example, which I find very, very useful, is also for studying the habitability of solar system planets and extrasolar planets. And this is the snowball Earth scenario. If you look at the Earth as it is now, more or less, or has been for the past several billion years, in principle, there are even two stable climate states. The temperate climate state on the right-hand side that we all know and love, hopefully, and the snowball Earth scenario on the left side. And the snowball Earth scenario really means that you have a global glaciation event. And we know that this happened at least once on the Earth. We have geological records that strongly suggest it. And why is this? And we have also several trigger mechanisms that seems to tip the Earth into this less habitable regime. And one of these scenarios, which is also relatively well understood, which was 0.7 billion years ago, is the so-called Neoproterozoic or late Precambrian snowball Earth scenario. And one of the reasons we think why this happened is because here the continental mass is kind of accumulated in the southern half of the Earth. After 1 billion years, where everything was nice and warmy, suddenly this happened. And what this happened is, in principle, what happened at some point, there was so much ice forming on these continents that you basically end up in this ice albedo feedback loop. There's a very interesting and very nice model, which in principle works with this simple equation here above. So this equation on the left-hand side basically tells you how much irradiation can actually enter to the system and form the planet. And this is the incoming solar flux. 1 minus A, where A is the albedo, and albedo can be between 0, ice-free, and 1, completely covered with ice in principle. And if you increase the albedo, right, then this left-hand side goes down. And the right-hand side gives you what the atmosphere is making of it. So here's the feedback from the greenhouse gas and the temperature. And we typically assume that the glaciation happens faster than the atmospheric CO2 can follow. So if you increase the alpha albedo, which means you reduce the incoming radiation, your temperature goes down. And that is, again, it's a feedback loop. When the temperature goes down, you get even more ice, which means you get an even higher albedo, and all the way down until everything is covered with ice. It has been pointed out, for example, in the Neoproterozoic age, that here the sun was even emitting 7% less energy than today. So it was actually pretty close to the snowball Earth scenario. And this landmass accumulation didn't help, and it basically tipped all the way down here. Problem then is, in order to get out of this, it's actually pretty difficult. So in principle, if you go with a simple model of this energy balance model, which is a very simple 1D model, you have to accumulate at least 100 times the amount of CO2 that we have now in the Earth's atmosphere in order to go all the way back to an actually completely ice-free scenario. And this is happening because in this noble Earth scenario, in principle, everything is covered with ice, so you have no surface weathering. So the sink terms basically vanish. But however, the volcanism, the geological activity persists. It takes however time. It takes about a few 10 million of years to actually get out of this and accumulate enough CO2 into the atmosphere to allow to melt this noble Earth scenario. And this is a bit of a conundrum that people also have tackled, because it's a bit of a problem, because you have to wait so long to get out of this noble Earth scenario. Is there a way to achieve this faster? And one of the ways, ideas that are floating around is the so-called water-belt Earth or slush ice bowl scenario, where you principally say, okay, let's assume that we have a tiny strip, let's say 10 degrees, 5 degrees latitude along the equator, which is ice-free. Can we get out of the noble Earth scenario faster? And here's a 3D GCM initialization from Abbott 2011. And here with the CO2 fraction. And when you start with the ice-free, if you basically neglect the ice, you can get from the snowball up here easily. If you are in the snowball Earth scenario, so the green circles, you really have to increase a lot. You don't get out of the snowball, you can't melt it really easily. If you have this tiny strip of water belt here, you actually only need to increase the CO2 fraction by a factor of 10, not 1000, and you get out of the snowball Earth, which means that life that already existed back then didn't have to sustain that long, actually have to wait that long to have a more habitable condition. And you can actually understand why it is so much easier to melt a snowball Earth by looking what you do when you want to microwave frozen food in a microwave or heat it on a stove. A little bit of water helps basically, because water is easier to heat up than the frozen ice lattice, where it is really difficult to actually make the molecule excited and to heat up. However, the noble Earth scenario really has to be looked at 3D climate simulation, and it turns out that it is really, really difficult in a 3D climate state to keep this stable. And the reason for that is, in principle, the narrowness of this water belt. So the water belt is 5 to 10 degrees plus minus latitude, but the Hadley cell, so the general is a circulation cell, which, as I remind you, depends only on the rotation period of the planet, which doesn't change. It's still 24 hours rotation period. It's larger than that, so it's a plus minus 30 degrees. So you have to basically maintain a mini water cycle in this relatively narrow region, which is embedded in a larger circulation cycle. And that is pretty difficult to achieve in a 3D climate state. So, but however, there are many uncertainties there involved, depending on how you actually move stuff up and down, what the albedo of the sea ice is doing, and how the cloud formation works. The other end is also important for understanding habitability, which means, okay, now you go, you say, like, okay, we don't care, we will have this noble Earth, and you just accumulate enough CO2 to melt everything. And then you tip, however, all the way over to a super greenhouse with an average surface temperature of 40 degrees Celsius, which to my taste is actually too close to the runaway greenhouse. I mean, you only have to go 10 degrees, 15 degrees warmer, and suddenly you're in the runaway greenhouse and can become completely inhabitable. So also on top of that, you have to think about the habitability of the planet. You have, the life already had to survive basically everything being frozen over, and everything basically towering out and towering up. And now on top of that, the oceans start to acidify, because as soon as you increase CO2 that much and the water and the surface ice starts to melt, you actually pump a lot of CO2 into the oceans, which means they're very acidic, and that's also not nice for the life that wants to survive there, especially if you have a carbonate shell. However, very recently, a new study has coming out that basically says, okay, fine, but as soon as you start to melt surface land, you also start to kick off surface plants. And surface plants actually take also up a lot of CO2. On top of that, if you properly model the ocean feedback to the CO2, that kind of helps to make the super greenhouse not super warm. So we will not go to the 90,000 ppm, but more to 30,000 ppm. It's still a super greenhouse, but not as extreme as if you would neglect this scenario. So also here the biosphere kind of buffers this extreme response, hopefully, and then the planet can be habitable in this regime and also go back to a more moderate temperate climate, which is also better for long-term habitability. So the idea here is that the snowball Earth scenario, especially the 0.7 billion years ago, is quite important to understand also other scenarios, because the benefit of this near-Proterozoic or the other age is that we have geological evidence. So we understand more or less what happened, where the land surface path was, where the glaciation was, how much the CO2 actually was more or less. And that helps us to understand, for example, the emergence of life on Austrian Earth, where we know that 2.5 billion years ago, the sun was even fainter. So it was 0.7 to 0.8 times the first solar flux, and we still had some habitable conditions, but we don't know the land surface, plate tectonic state, and the greenhouse content there, because we are on a geologically active planet. So a lot of the evidence has been basically destroyed. And on top of that is early life also kind of gives us a wild card, because early life tended to also produce methane, and methane is also a greenhouse gas. So this is really important. So, but also here, the 3D climate models are really the forefront, because 1D models really don't explain that you can have surface liquid water and therefore life in this early stage. And of course, the understanding snowball Earth, which basically, if everything is covered, kind of resembles the icy moon stage in Europa. We also, in principle, hope that we have surface liquid water and some life down there. And of course, the faint young sun paradox becomes even more important for early Mars, which has the double problem. It is the sun. We know that surface liquid water existed, but we also know that the sun back then was less luminous than today. At the same time, Mars is also farther away than the Earth, which means we have the double problem. However, the nice thing, rotation period of Mars is pretty similar to the Earth. So in principle, it's not difficult to adapt Earth climate models to the Mars. And when we do this and try to understand surface liquid water, however, one problem is like, okay, let's just pump up more CO2 in the system. It works for the snowball Earth. Would it work for Mars? However, it turns out it does not. And the problem is the CO2 ice clouds. You cannot have a dense CO2 atmosphere without some point the ice clouds forming. And the ice clouds actually cool the atmosphere. And this has been a study done by François Forget et al. I think 2012. And they have shown that you cannot get, under any circumstances, with a pure CO2 atmosphere, surface temperatures above 0 degrees Celsius. So you cannot get surface liquid water with this. However, recently there's a new evaluation there also happening. And one of the idea is that, okay, maybe not with CO2, but what about hydrogen? At the beginning, when I introduced the habitable zone concept, I told you already that hydrogen is a powerful greenhouse gas. And people have looked at it in the recent years, and it turns out you don't even need to put that much hydrogen. So let's say 0.1 bar of hydrogen is enough to give you a very strong enough greenhouse effect to have surface liquid water. However, now it depends strongly on atmospheric erosion. So how long does it take actually to maintain this hydrogen component of the atmosphere that you actually need for surface liquid water? On the other side, from the geophysical part, it has also emerged in the past years that the smallness of Mars and the mantle state that actually is more reducing tends to promote H2 outgassing from the mantle. So there is some evidence also from the geophysical science that hydrogen might here be the solution for the young sun paradox, because pure 3D climate simulation with CO2 doesn't do it. And 3D climate circulation becomes also, of course, important if you want to understand other worlds. And here, very important is the TRAPPIST-1 system, which is a quite nearby system. And 3 planets are in the habitable zone, which means in principle they can have surface liquid water. But you can also see here that this is a weird system compared to the solar system. So the host star is very small, which means all these planets are very, very close to the host star. So it is a very tiny mini system that you can basically completely engulf in the Mercury in an orbit. And this means that all these planets are tightly locked with the host star. So we have eternal day sides and eternal night sides. And when people envision tightly locked Earths with this scenario, they come up with this artistic view, or they put the Earth in there. Actually, putting the Earth in there is better because this artistic view is just wrong. It's just completely completely misunderstanding of how and that completely ignores 3D climate. So it's purely coming from 1D model, basically assuming that we have hot air and it's basically is nailed to the ground. But hot air is not nailed to the ground. Hot air actually rises and goes to regions of colder temperature, which is the night side. So it has been pointed out since 1997. So over 20 years ago, since over 10, we know that we have to have an exo-Earth and put it into tidal locking. We have a very, very efficient heat transfer that acts to very nicely make the temperatures in the surface and the upper troposphere very, very balmy. So suitable for surface liquid water. So the tidal locking in itself is not an argument against efficient heating. And also this view is completely wrong because this is basically the tropical headley circulation wrapped around the whole planet because the rotation period is equal to the orbital period. It is very slow, which means it is one giant headley cell. And headley cells are known for being extremely good in transporting heat and other stuff. Okay, and also have been studies of how thin has the atmosphere have to be to not freeze out on the night side. And there have been 2 major studies here, and in principle this view stands. If you have surface pressures more than 140 millibars, or more than 10% of the Earth's surface pressure, you're good to go. The atmosphere will not freeze out. Nitrogen will not condense out of the night side. It will be fine. The same with water, but what about water? Can you maintain a water cycle on such a planet? And there are 2 things. If you have an ocean which is thick enough to connect via currents the night side and the day side, you're good to go. That's the lobster ocean scenario here. The oceans are extremely good, even better in circulating heat than the atmosphere. So if you have a global ocean, there's no problem at all in maintaining liquid water, even if the night side is very cold. If you have basically the whole thing there's little water, then at some point, and that is here the scenario, you might get problems. So, and I mean, at some point, you really start to accumulate water on the night side, this water trap configuration down here. But you really have to go to less than 0.4 times Earth's ocean. And here it was also neglected that you might have other effects like tidal heating, which would have an additional heat source. Because in principle, if you have enough water, you still melt enough ice on the edges of the night side cap that will flow then towards the day side, that you will not squeeze out all the water and accumulate it on the night side. That is just not happening. Again, because of circulation machines. But here now, basically assuming that water and oceans also have circulation, and also there, hot stuff wants to equilibrate with cool stuff. So, in a nutshell, tightly locked exo-Earths, if you just put an Earth in a tidal locking and look at the water cycle and into the climate regime, should be habitable. Especially at least for reasonably big atmospheres between 1 to 10 bar, so pretty Earth-like, and also for an Earth-like water content. So if you have more than 0.5 terrestrial oceans water equivalent on the surface, you're good. Another point which is important when we understand the habitability of planet is how far inwards can we go? And here also tidal locking is very important because it gives us a viewpoint, it gives us a different viewpoint from the Earth. So Earth is a fast rotating planet. Tidal locking planets are pretty slow rotating and always facing the day side, the stars with the same side, so they have an eternal day side. And how do you actually end the habitability of the planet if you are very close to your host star? We know this from Venus in the solar system by the runaway greenhouse. And I already told you a bit about with the super greenhouse and the tipping point of the ice albedo feedback. If your surface temperatures on average are larger than 50 degrees Celsius, then you evaporate too much water vapor, which is a powerful greenhouse gas, which evaporates more water, which makes it even more powerful, and you get all of the ocean out there. And on top of that, you evaporate the water vapor into space. So photolysis will break up your water vapor into hydrogen, oxygen. The hydrogen escapes easily into space within 100 million years, and you end up with a Venus, especially since also the silicon cycle will go it afterwards. And there have been various ways of trying to say, okay, but is there a way to prevent this runaway greenhouse? And one idea was basically to make the planet dry. So basically have a very, very low water content. But then we run into the problem that I showed you earlier about the water freezing out of the night side. So it's probably not a good way to go. However, there's something else which actually comes naturally out of the 3D climate state of these planets that really helps you to push the planet pretty far inward, and which is the cloud formation. So this global Hadley circulation cell, where you have the upwelling branch on the day side focused, is a very efficient cloud machine. With a cloud machine with an albedo of 0.5. For comparison, the Earth's albedo is 0.3. So you already have here a situation where you basically equip the planet without doing anything with a natural sun shield. And that has been pointed out by Young et al. In 2013, 2014. And with this equipped, he basically now looked and reworked this habitable zone regime that I've showed you earlier with Sarah Seeger work, which was based on a purely 1D model. And again, I show you on the y-axis the temperature of the star, which means we have hot F stars down to very cool M dwarf stars, where the TRAPPIST 1 planets are. And the stellar flux normalized over, so stellar flux over the solar incoming flux today. And 1 means our current Earth. Our Earth is over here. And the solid green and blue line gives you the 1D habitable zone estimates. Now, this has been reworked several times with 3D climate models, and you can already see here, if you just put a 3D climate model on a rapidly rotating planet like the Earth, you already are able to extend the habitable zone further inwards, so have actually more planets that are potentially habitable here. But if you have now tidally locked planet or a slowly rotating planet, you actually you gain quite a lot of possibility of habitability. So you can really push the planet all the way very, very close to the host star, just because this cloud regime, so this cloud machine is so efficient, the albedo is so high, that you can really, really push the planet much further inwards, which is not the case with the Earth, because Earth is patchy. So the clouds basically, there's too much holes in the cloud, and they are all over the place, night side and day side. And here, this is the sunship just predominantly over the day side. And this 3Dness basically helps you to maintain a habitable climate for larger incoming irradiation. And the interesting thing is here that this work basically had feedback effect of re-evaluating the habitability of the solar system. Because people were like, okay, slow rotating and tidally locked planets. Venus. And Venus is here, right? So Venus and early Venus. So again, here you have to take into account why Venus and early Venus are not the same. The sun has evolved. So 2 billion years ago, the solar flux was smaller. That's why early Venus was actually closer to the habitable zone than Venus is now, because now the sun is much more luminous than it was back then. And based on this work, principle, people were like Michael Way, for example, said, okay, was the early Earth habitable? And if you put a 3D climate model on the early Venus and assume Earth-like condition, yes, in principle, you actually get habitability, at least for a few million years. Venus has other problems as well, but at least from a 3D climate viewpoint, there's nothing speaking against early Venus being inhabitable 2 billion years ago. So that's funny thing about these exoplanets, that by putting our 3D climate models on different configurations, we start to re-evaluate the habitability of the solar system planets, in that case Venus, which people basically say, Venus was never habitable, right? So now the habitability of tidally locked exo-Earths, where we have the TRAPPIST planets, specifically TRAPPIST 1e, which is one of the inner planets of this habitability, which means that it's one of the planets that is also easier to observe, because the more observations you accumulate, the better. So if you have a relatively short period habitable planet, like TRAPPIST 1e, it is a prime target for characterization. However, it has been pointed out that the sun sheathing effect, so this cloud machine, depends strongly, especially for this rotation period, depends strongly on the wind sheds that can arise alongside it. So TRAPPIST E actually has a relatively short orbital period of 6 days. And me and other people have pointed out with such short orbital periods, you also get not only the cloud machine, but wind sheds, and they can be less or more strong. And that means, again, we have a big stability of climates. So you can very quick, with very tiny changes, go from one climate to the other. And one is better for the cloud machine and one is less good. And this has been actually confirmed also with more complex climate models, where I show you the work of Dennis Sergeev, where colleagues basically come together with the Earth-like climate models adapted for TRAPPIST 1e and compared what the climate would do and what the cloud coverage would do. And here in this one climate state where we have in principle an unencumbered, where the wind sheds are relatively moderate and do not impact the headless cells or the cloud machine strongly. You see here the view on the day side of the planet, where here we have between 90 degrees west and 90 degrees east, the day side. And here, these plus minus 90 degrees is these are the planetary limbs, which are important for understanding atmospheric characterization. And here is the water evaporation. You see here the day sides are in all cases evaporating the majority of the water, and the cloud fraction. And here, however, you see also different differences between the different climate models. Most of them tend to agree that the day side is pretty cloudy, so almost up to 100% cloud fraction. However, the limbs, the planetary limbs, they can be partly cloud-free. And let's look at the other climate state where we have wind sheds, and here you see it quite strongly, the impact of the wind sheds. Now this cloud machine, in this case, is particularly disturbed, you could say. So still here we have still a strong cloud machine, and it's exactly the same atmosphere composition, everything's the same, it is just a different climate model. And here the differences are pretty drastic. So some of them don't have actually any problem. We still have a day-side cloud coverage. For other cases, it seems to be more smeared out, more clumpy, which means here, at least, it seems that we have at least partly cloud-free day sides. But still, the majority of the models seem to indicate that, again, at least part of the planetary limbs should be cloud-free. And what does it mean for observations? So you have two major things how we probe an exoplanet atmosphere. We either look at the emission of the planet itself, which means that you're looking mainly at the day side. If it is a climate one, the very efficient cloud machine, you won't probably see a lot because it will be clouded out. If you are probing, if the planet is transiting in front of its host star, and we are able to basically measure the atmosphere via the interaction of the stellar light going to the atmosphere directly in transmission, you're basically probing the planetary limbs. And there's a high chance in both climate states that they might be reasonably clear, which means, in principle, my money is on transmission spectra. And here's a work from Lucy Jäger, 2022, who basically investigated how an Earth-like planet would look on TRAPPIST 1e, and what specifically what would happen if the silicate weathering feedback would become weaker and weaker, right? The silicate circuit becomes less and less and less, which means that the CO2 abundances are rising. And this is the outcome in transmission. And the signal of the CO2 at 4.3 microns is very strong. And if you have 100 transit observations, you have accuracies of 10 ppm and less. And then you can really start not only to actually see that the planet has an atmosphere, but also if there is silicate weathering feedback, if it is, which is really one of the important factors of making a planet habitable. We also have the work in review where we are thinking about, okay, do we actually have also feedback to the biosphere? Because more CO2 also means that we have more land plants. More land plants might actually also help to buffer this feedback effect, and more also maybe we see some methane. Maybe next month I can tell you a bit more about it when we have passed the review. But for now, I want to finish with this plot, because since last week, we actually know that at least one rocky exoplanet has an atmosphere. So this is an observations from Renew et al. With the planetary mission, and these see for these planets CO2 gas. So the 4.3 micron, this feature is pretty strong and pretty robust. So 55 Cancri E might have CO2 gas on an atmosphere, which, however, is a bit of a problem for geophysicists, to be honest, because 55 Cancri is super hot. It is orbiting very close to its host star and has surface temperatures which are larger than 1,500 Kelvin. And it is very old, so it's an 8 billion years old system, so twice as old as the solar system. So how are we even able to have CO2 gas on such a planet? Also, to be fair, observations of 55 Cancri are very variable. So whenever we look at it, it gives us something different. So 55 Cancri is really not habitable. However, it really helps us to redefine our geophysical atmosphere model. And also it shows us, yes, we are in principle able to see the atmospheres of rocky planets. And when we do see this, then we can put our 3D climate models, our geophysical models, our biological models to work and understand these worlds, which are not Earth-like. So, and we know this because the 3D climate tells us where the surface water, the cloud, and also the ozone is going. And because of this, we also understand, or hope to understand, that we can see, at least at the planetary limb, which are transition spectroscopy, the silicate cycle, and the biosignature. And if we are able to see part of it with a huge time investment of 100 transit, which means 600 days of observation time and more, I think we are pretty good to go for future space missions. And with this, I would like to end my presentation and take your questions. Thank you for your attention.